This time you've got a beam with an overhang. So it's a little bit like a springboard in the swimming pool, those old style springboards. And so you've got a pin connection at one end and you've got a roller at the other. So what I did was, I drew my free body diagram, didn't label it, I should have. So this is my free body diagram. And then what I did was figure out my reactions, but I thought I'd show you one example where you actually get that wrong. So say I guessed that this reaction was upwards, and so I've worked through my calcs and I've figured out that actually RA is the other way. So what I would usually do here is I would go back through and I would correct that. I'd put it the right way up to start with and correct it so that it is shown the right way around, because you need them to be the right way around when you get to the shear force diagram. And so this one, it's saying I've got through this, I've got RA is negative. That tells me that I've got this arrow the wrong way round. And so what I really need to do is to put that the other way, like so. And this is RA, and this is point A. And then just go through my calcs and make it the right way around now. So in fact, RA, that would have been positive. That would have been positive, and so you would have been dividing by 3 instead of -3, and so therefore you would have got a positive answer at the end for this direction. Okay, so just showing you what will happen. So if you come through all this and you're using all the right sign conventions for all your forces and you find that it's negative at the end of the day, that means what you drew on was the wrong way round, and you need to draw it the right way round so that it makes more sense when you're working through the shear force diagrams. So let me draw my shear force diagram and bending moment diagram axis, and then I'll get back to you. So I've drawn those now. Remember, the moments downward for positive. Say it 1,000 times, maybe everyone will remember, but I bet they won't. I bet some of you will forget. Anyway, enough of my moaning. So we're following the same rules as usual. This time though, we've got an interesting situation where we've got uplift at this end, so it's trying to pull this up. Let's just think about the deformed shape of this thing. It's kind of interesting. So what it's actually going to do, this springboard, is it's going to go something like that. And so we'd be expecting, actually it's kind of hogging the whole way. It's always curving down the way. It's always curving that way. And so it's kind of it should be hogging all the way. So therefore it should be a negative moment all the way. Shears, well, we should start off with a negative shear because we've got down on the left and up on the right. But here it should become a positive shear because we've got up on the left and down on the right for this section. Okay, so we're kind of thinking about the deformed shape before we start when we're trying to figure out what these shears and moments should be. Then we're going to use a rule, so you follow the forces. So it's pushing us down, and it's pushing us down by 6.67 kilonewtons. Now, should be 4 significant figures, but I'm not going to combine these, and so I don't want it to be messy. So I've just kept it to the same number of decimal places for both, so they'll kind of cancel out. It wouldn't matter. Whatever you did would be fine. So 6.67, where's that? 7.5 would be in the middle, somewhere like that. This would be negative 6.67 kilonewtons. So it's a negative for the shear. And then nothing between, so there's nothing happening until it gets to the reaction, so until it gets to that roller. So it keeps going flat. This time I've lined them up to make sure I don't make the same stupid mistake again. Then it's going to go up by, RB is 16.67, so it's going to go up to 10 kilonewtons, sorry, and shear, 10 kilonewtons. I haven't left myself much space, but that's okay. Then it's just going to go flat because there's nothing happening. This is 10 positive, 10 kilonewtons. Then it hits that force, the applied force, which might be the person jumping off the end of the springboard or something. What is that though? 10 kilonewtons, you'd have to weigh about a ton though, so maybe not. Maybe it's an elephant jumping off the end of the springboard. And that's our shear force diagram. Too easy. Like I say, shear force with forces is easy, just follow the forces. But you keep in your head, keep thinking back to what shear really means, and so you've got to look at the signs of your forces to make sure it all makes sense. Now then, for the moment. So there's a pin at this end, so it must start at 0. So there's no moment at the end there, so we know that much. Switch to blue for the moment diagram. So there's a pin at that end, and then so the shear is negative 6.67. So we need to be going in the negative direction for moment, which for a moment diagram is upwards. For each meter we go along, we need to go 6.67 kilonewtons, but at this time it's actually going to be easier if we just do the whole thing. So if we were to go 3 meters, it's the area between the 2 points you're thinking about. It'd be 6.67 times 3, which is going to be 20, I think. 6.67 times 3, yeah, I think so. And it's minus 20. So 10, 20, we'll just see what happens here. See if I've got enough space on my diagram. And so by the time I've got to, now just be careful. It's a moment diagram, so they're negative. So 30. And we know that it says straight line because it's a rectangular shear force diagram, or you can think about it, look, each time I go 2 meters, it's going to be the same. It's not like those points are always the same distance apart, so it's going to be a straight line. Whereas if this was triangular, the area would keep changing, so the amount the moment diagram changes, the bending moment diagram changes, would also be changing, and that's how you end up getting a curve. For the next one, we need to be heading in the positive direction because it's a positive shear. For each meter we go along, we're going to go down 10 times 1, 10 kilonewton meters. So 10 kilonewtons times 1 meter, 10 kilonewton meters. So it's going to be a bit like that. Black, I wanted it to be blue. A bit triggering if it's not all the same colour. Let's do it all the same colour. Moment diagram is going to be like that. And again, you can see this rule where the peak moment occurs at zero shear. So you're getting well, actually it's a minimum moment in this case. It's the most negative it gets. Minimum moment occurs at zero shear. This one doesn't really have a zero shear, so it's a little bit different. It doesn't cross the axis at any point, but this one does, and the first one did as well. Zero shear, maximum moment in this case because it was hogging. This one's, because it was sagging. This one was sagging because it was that shape there. I drew it, sagging. This one down here is hogging, so it's all negative, so you're getting a minimum moment. And again, that minimum moment is occurring at, well, it's where a support is. It's where, but in terms of the free body diagram, it occurs at a force if it's all point loads. Shade it, put on that peak value, remembering it's negative, minus 20 kilonewton meters. This is going on a bit long now, so I'm not going to do a check on that one. I'm pretty confident it's okay because I came back to 0 at the end here, so I'm pretty confident that that's okay. Similarly for the shear force, it came back to 0. But if you want to do a check, do it just before the 3 meters. Do a check on what the moment should be just before you get to that support and check that it really is minus 20.